In the previous slides, we reviewed Boyle's law, which states that the volume of a gas is inversely proportional to the pressure when we keep the temperature and the amount of gas constant. We then discussed Charles' law, which states that the gas volume is directly proportional to the absolute temperature when we keep the pressure and the amount of gas constant. We could also have mentioned the much more intuitive Avogadro's law, which states that at constant pressure and temperature, the volume of any substance is directly proportional to the number of moles of substance. So, from these observations, we can see that there must be a single equation which summarizes all these observations and expresses how the volume of a gas varies with pressure, temperature, and number of moles. Such an equation is known as an equation of state, as it describes how the various state properties of a substance relate to each other. Every pure substance can be described by a particular equation of state. Late in the 19th century, scientists drew the truly amazing conclusion that under the specific conditions we will discuss in the next lecture, all gases obey the same equation of state. In other words, under specific conditions, the relationship between P, V, T, and N is the same for all gases. This equation of state is called the ideal or perfect gas equation of state. To derive this equation of state, we simply need to recall that V is inversely proportional to P, that V is directly proportional to T, and finally that V is directly proportional to N. Hence, V is directly proportional to the quantity N times T over P. Since this relationship is independent of the chemical structure and composition of the gaseous substance, we can state that the ratio of P times V over N times T is equal to a constant. This constant is called the universal gas constant and is denoted by the letter R. The ideal or perfect gas equation of state is therefore written as PV equals nRT. If we use SI units for all quantities involved in this equation of state, that is, we express the pressure P in Pascal, the volume V in cubic meter, the absolute temperature T in Kelvin, and the amount of material N in moles, then the universal gas constant R is approximately equal to 8.3145 Pascal times cubic meter over mole times Kelvin. Since the product of Pascal and cubic meter is a joule, we will remember the value of R as 8.3145 joules per mole Kelvin. If, on the other hand, we choose to write the ideal gas law with the pressure expressed in atmosphere and the volume in liters, then the universal gas constant R is given by R equal 0.082058 atmosphere times liter over mole times Kelvin. We should note that there are equations of states for liquids and for solids. However, these equations of states are more complicated than for gases and involve parameters that depend on the actual chemical structure and atomic composition of the substance of interest. We will learn in the next lecture that the increased complexity, characteristic of equations of state describing the liquid or the solid state of a substance, results from the existence of strong interactions between the molecules or the ions making up that substance.